We will now discuss solution of two-dimensional problems in the form of a Fourier series. This discussion is in the continuation of plane stress problems. We will try to employ stress formulation. The previous two examples of simply supported beam and a fixed-ended beam were solved using polynomial functions. Polynomial functions are good at handling those loads which are uniform or which are continuous. However, if we have a complex set of loading, especially a discontinuous type of loading, then the rate of convergence of Fourier series is very high as compared to the polynomial function. Let us see how the stress functions can be derived in terms of trigonometric functions. So this is our compatibility equation written in terms of x and y. It is partial 4 phi by partial x4 plus 2 times partial 4 phi by partial x square partial y square plus partial 4 phi by partial y4 equal to 0. This equation is considering that body forces are 0. So we define our stress function equal to sine m pi x over L times Fy. Thus, we have separated our terms into x and y, and both terms are getting multiplied with each other. As we know from our previous discussion that by separating our variables in this fashion will help us get ordinary differential equations in the end. This function sine m pi x over L is analogous to half-range sine Fourier series. We are taking only one term of our half-range sine series and we are considering the weighted factor equal to 1. In the case of half-range sine series, we are dealing with only half period of the function. Thus, we are integrating our function between 0 and L. We can call m pi over L as alpha and plug the values in the compatibility equation. Thus, we will get equation alpha 4 f of y minus 2 alpha square f double dash y plus f4 y equal to 0. This is a characteristic equation, and from this equation, we can get our function f of y equal to c1 cos hyperbolic alpha y plus c2 sine hyperbolic alpha y plus c3 y times cos hyperbolic alpha y plus c4 y times sine hyperbolic alpha y. We can plug the values of fy in our phi equation and we will get phi is equal to sine alpha x times small bracket c1 cos hyperbolic alpha y plus c2 sine hyperbolic alpha y plus c3 y cos hyperbolic alpha y plus c4 y sine hyperbolic alpha y. After finding out phi, we can use Airy stress function to get our sigma x, sigma y, and tau xy. In this example, we are using xy coordinate system rather than x1, x2. Thus, sigma x comes out to be sine alpha x, big bracket, c1 alpha square cos hyperbolic alpha y plus c2 alpha square sine hyperbolic alpha y plus c3 alpha times small bracket 2 sine hyperbolic alpha y plus alpha y cos hyperbolic alpha y plus c4 alpha times small bracket 2 times cos hyperbolic alpha y plus alpha y sine hyperbolic alpha y. Sigma y comes out to be minus alpha square sine alpha x small bracket c1 cos hyperbolic alpha y plus c2 sine hyperbolic alpha y plus c3y cos hyperbolic alpha y plus c4y sine hyperbolic alpha y. Similarly, tau xy comes out to be minus alpha cos alpha x times c1 alpha sine hyperbolic alpha y plus c2 alpha cos hyperbolic alpha y plus c3 small bracket cos hyperbolic alpha y plus alpha y sine hyperbolic alpha y plus c4 small bracket sine hyperbolic alpha y plus alpha y cos hyperbolic alpha y. After finding out the stress components, now we can use the boundary condition to get our constants C1, C2, C3, and C4. So, for example, consider a case where we have load in the form of sine wave applied at the top and bottom of the wall. We have a coordinate system xy shown in this figure. The origin is starting from the left side of the wall. The distributed load can be written as A sine alpha x at the top and B sine alpha x at the bottom, where alpha is equal to 4 pi by L. A and B, the amplitude of sine wave at the top and bottom of the wall. Alpha will be equal to 4 pi by L. Since we have two full sine waves, therefore we can write alpha times L is equal to 4 pi. And from there, we will get alpha is equal to 4 pi by L. Now we can apply the boundary conditions and get our constants. So the first boundary condition is that at y is equal to plus c, tau xy is equal to 0. Thus there is no share at y is equal to plus c, and sigma y is equal to minus b sine alpha x. The reason sigma y is taken minus is because during the first half of the sine wave, we have got compression, and according to our convention, tension is considered positive. Similar argument apply at y is equal to minus c, i.e. we have tau xy equal to 0 and sigma y equal to minus a sine alpha x. Now these values can be substituted in this equation. We can get C3 equal to minus C2 times alpha cos hyperbolic alpha c divided by cos hyperbolic alpha c plus alpha c sine hyperbolic alpha c, and C4 equal to minus C1 alpha sine hyperbolic alpha c divided by sine hyperbolic alpha c plus alpha c cos hyperbolic alpha c. Now we can write this second condition, which is sigma y is equal to minus b sine alpha x and sigma y is equal to minus a sine alpha x. And the four constants comes out to be C1 equal to a plus b by alpha squared times sine hyperbolic alpha c plus alpha c cos hyperbolic alpha c divided by sine hyperbolic 2 alpha c plus 2 alpha c. C2 comes out to be equal to minus a minus b by alpha square cos hyperbolic alpha c plus alpha c sine hyperbolic alpha c divided by sine hyperbolic 2 alpha c minus 2 alpha c. C3 comes out to be minus a minus b by alpha square alpha cos hyperbolic alpha c divided by sine hyperbolic 2 alpha c minus 2 alpha c. C4 is equal to minus a plus b by alpha squared times alpha sine hyperbolic alpha c divided by sine hyperbolic 2 alpha c plus 2 alpha c. These can be substituted into our sigma x, sigma y, and tau xy, and we get the final form of the three equations. Now we have worked out all the constants, and all the stresses can easily be worked out by plugging the constants in our stress equations. So instead of this type of function, we can have any other type of function which can easily be accommodated by our stress function. So imagine if we have a function at the top and bottom in the form shown. In this case, we have to convert the top and bottom loads into Fourier series. Once these are converted into Fourier series, then we can get our boundary condition in a similar manner to the sine wave problem. We can also find out our stresses if we have a pointed load. In the case of pointed load also, we can convert it into an equivalent UDL patch load. And after that, use Fourier series to approximate this load and get the values of our stresses. Thus, we can see that Fourier series can be employed to approximate different types of loadings. Imagine we have a problem shown over here in which we are given loads on a bunker wall. We have got a load per unit area applied along the length L at the top of the bunker and a patch load at the bottom of the bunker. We are asked to carry out stress analysis of this problem. So this is similar problem to what we discussed over here. We have already worked out the stresses in the form of constants C1, C2, C3 and C4. All we have to do in this case is to convert these loads into Fourier series and then use the boundary condition to get our final stresses. So this will be similar to what we have over here. We have got a load, and this load at the top, both at the top and bottom, can be converted into a Fourier series. And then we can use this approximate function to get our boundary conditions and finally determine our constants. So this load, which is a patch load, can be approximated into Fourier cosine series. As we can see, this is a even function. In this case, we have the overall period between 0 and L. So we can take just half length of this wall as half period. We can work out our constants and get an approximate function for the patch load. We can carry out similar exercise for the top load, and after that use the boundary conditions by considering sigma y equal to the Fourier series which we would have derived. We would have four equations and four unknowns in terms of C1, C2, C3 and C4. They can be worked out. Then the constants can be plugged back into our airy stress functions and we can get the stresses in the system. In a similar manner, we can have a beam which has got a cosine load. So this is also a similar problem to this one. So instead of a continuous sine wave, now we have a single cosine wave having a period 0 till L. Surely this can be solved using the cosine Fourier series. So the amplitude is P1 and alpha will be equal to pi by L. The half period will be equal to 0 to L. As we discussed, we can have f of y worked out in terms of cosine and sine hyperbolic trigonometric functions. We can have our airy stress functions worked out. After that, we can plug the boundary condition. The boundary condition this time would be at y equal to plus c, tau xy equal to 0, and sigma y is equal to minus q time cos alpha x, where q is taken equal to p1. At y is equal to minus c, we can take tau xy equal to 0 and sigma y equal to 0. Noting that in this case, we are taking x-axis in the horizontal direction and y-axis vertically up. Therefore, sigma y is equal to 0 at the lower boundary. As we can see, there is no load applied at the lower boundary. Four equations and four unknown will give us constants C1, C2, C3 and C4. We'll plug back these constants in the airy stress function and work out our stresses. In part 2 of this question, we are asked to show that when we apply similar load at the bottom, then two of the constants of integration would come out to be 0. And let us see how we get two of our constants equal to 0. If we place another load at the bottom, which is opposing the top load. That would mean the fiber associated with the x-axis will remain straight. Thus, we can say that any quantity varying along y must be an even function with respect to x-axis. In other words, fy must be an even function. Thus, from symmetry, we can say that fy must be an even function. So, all the terms which are odd in our fy function will have to be 0. C1 cos hyperbolic alpha y is an even function. C2 sine hyperbolic alpha y individually is an odd function. C3y cos hyperbolic alpha y is an odd function, and C4 sine hyperbolic alpha y is again an even function. Thus, we can say that the term 2 and term 3 must be 0 because they are odd function. Thus, C2 and C3 must be equal to 0 by inspection. So Fy will be equal to C1 cos hyperbolic alpha y plus C4 sine hyperbolic alpha y. Hence, by symmetry, we will eliminate the two constants.